Okay, welcome everyone. So we continue the session today, the fourth day. So this is the first lecture will be given by Arnav.
So today we will start with model examples of stochastic heating heats. So this is whatever we have learned. So now we can apply figure. The quantity we need to derive, say for example, typical characteristics of this kind of machines is efficiency, of course. For that, whatever tool we need, we have now, like work, heat, internal energies, right? They are all well defined for a process, and we can apply those things to here to get, and we have to make the process cyclic. That's the most important thing for an engine, right? So before going into stochastic thing, we just recapitulate a little bit what we have basic macro heating units, right? So this is a well-known example that if we have Carnot, right? So this is TS diagram. Already I guess I mentioned it in this talk. So this is isotropic jumps, and these are the isothermal paths. Okay. So this is so how to calculate the heat. Say for example, this is the area of this rectangle. Correct? So this is simple. You have A. So this is the gauge, and this is DC line. So these are isothermals. So you have EH minus TC, and then you have the TDS. So you have SA. B minus C. Okay. So this is the total heat that, and no, this is the Q. So if some heat goes in H, then go out. You see these are the adiabatic or isentropic, so no heat transfer. So QH minus QC. So this is the heat goes out of the cycle, and this is coming in. So this is the net one, and then you have Q. What is the input? Is then EH. So theta is this is the simplest thing that we have done long back. Now you have there are some caveats, of course, because it's idealization. So it says that if you run it, so these are the things that we use in the reversible or quasi-static case. Right? Otherwise, you have to put some inequalities there. Now, the point is, see, if along this line, if the system is in equilibrium, that means the temperature of the working fluid inside and the temperature of the bath is same. Then the first question is how we get this UH at all. why this QH is flowing, because there is no temperature gradient. Correct? So that if there is no QH, no water. So efficiency is 0, no input, no output. Right? So that means that it is a very, very idealized condition. We have to run the cycle irreversibly so that some heat can go. That means that the fluid inside should have different temperature, say FH, while this, and while this it is say T, fluid but cold. So there is a difference between the fluid temperature. So this is TH, the bath hot temperature, and then there is a fluid hot temperature that should be or greater than 0. Then the heat flows. Are you with me? Is it? And then then there is a fluid colder temperature, say fluid C, cold, and then there is the actual cold temperature of the bath. That has to be greater than, no, this has to be less than 0. Then the heat goes out. Correct? Is it correct? So then this, if you include this parameters, so FHD, and then there is other things.
What is FH, what you are writing?
So there is a working fluid inside, right? In any engine, macroscopic, and there is a bath outside. So if there is a temperature difference, then only heat goes in or goes out. So these are the temperature difference between the fluid and the outside. Correct? Otherwise, no temperature can go in, no heat can go in, no heat can come out. So this thing, now you can idealize another step. So this is what we need. And then we assume also that if we assume that this fluid at the end with full cycle,
no, but
the entropy.
If I have isothermal expansion.
So if you have isothermal quasi-static case, there is no way to go, the heat cannot go in. So the Carnot system is an idealized system. It's an abstraction. Okay. So then, if you have this fluid in cycle, so if we assume that the entropy of the fluid is not changing over the cycle, so that is where the irreversibility comes. Okay. Then you can calculate. So if this parameter is say x, this parameter is say y, then your power you can write in terms of x and y. So this is the way what I'm stating is how you calculate a non-quasi-static macroscopic heat engine, the efficiency at maximum power. So once you write, so I'm not going through details, the reference is this American Journal of Physics, I forgot the year, but it's very common, we can just. So if you write this P, the power in terms of x, y, these are the x, all other variables are say constant. For example, cycle time, then, so they are all parameters, you say, okay? Cycle time, tau. Then very important parameters are the conductivity of this wall, okay? So we, deriving this P of x, y, we assume the heat flows proportional to x and it comes out proportional to y. So this is kind of Newton's cooling. So there are a lot of assumptions going on even if I calculate the efficiency at maximum power. These are the assumptions. Okay? So there is a difference between temperature, otherwise.
Can you please draw a schematic for this?
The schematic is same. The schematic is same as Carnot. But there are differences, like we have a fluid temperature which is different from the bath temperature. That is why the heat flows. Okay, this is one thing. Now, what is the quantification of the heat flow? That is, we say that the heat flows which is proportional to the temperature difference between the fluid and the bath. So this is a phenomenological law, right? So if there are other kind of cooling laws as well, cooling or heating law. This is Newton's cooling law. Okay, this, if we assume this kind of linear relationship between the heat flow and the temperature difference, and on top of that, another very important, which is not happen in the usual cases, that the working fluid is the average entropy is 0 over a cycle. Okay.
So, but this T and S you are plotting, I mean this T which you are referring for?
No, this is for Carnot. This T is the bath temperature. Okay. Now, if you have this, then you can. These are all parameters. So the conductivity of the walls are say alpha beta. So these are the places where the conductivity comes. Alpha, beta. And there is the cycle times. Say this is your time for hot isothermal, this is the time for cold isothermal. So the heat goes in is proportional to the heat conductivity, the constant, then this is the x, the difference, and then there is this tau time scale of the hot isothermal bath. So these parameters goes in here. This is the total cycle time tau, alpha, beta, and this function is of x and y, which is the temperature difference between the bath and the fluid. This you actually minimize 0 of this. The power is defined by this you calculate, this is the work divided by cycle time. So power is defined by Q input, QH, Q goes out like this. And it's all this your thing, you have this x, y. Finally you will get a function of x, y, the cycle time tau, conductivity is alpha and beta. This 0, and similarly this will give you another equation, simultaneously true. This, from this you actually get beta that mentioned earlier, 1 minus root over Tc. The very remarkable thing is this results are devoid of this alpha, beta, tau, etc. This is the P at the eta at maximum power. So you can say star. Because maximize because this process. So this.
I could have differentiated this with respect to tau also, right?
Yeah, but it is these are all parameters, these are functions. So this is the way that they have treated as independent variables and x and y. But there are interesting results you can get if you. So there are huge literature on this engine, which is I don't know
what is the difference is here?
This is American Journal of Physics.
Why?
Urso and Albon. Okay. Urso. I guess it is in similar time when this Parsons paper came out, that high viscosity thing, high viscosity swimmers.
But you had defined this x and y was T.
X and y is the difference between the bath temperature and the fluid temperature.
Sir, what is the cycle time?
What is that?
Cycle time, how do you manage?
You just fix it. You just fix it. Cycle time is like very similar to here, like Carnot. We start from an initial condition, then you go to a quote-unquote isothermal. It is like there is a difference now the temperature. So the system is not in equilibrium with the bath. That is why there is a heat flow from the bath to the system. Then again, so the diagrammatic picture of the Carnot remains same. But these assumptions are these things are crucial. That heat is now coming from the bath to actual heat is coming from the bath to the system, and we follow some kind of phenomenological law. It is Newton's law. That means your heat is proportional to the temperature difference and the conductivity and the time that you spend. So
this tau, this result is independent of tau.
Yes.
But I can't take tau equal to like a Carnot.
No.
That is all given.
Yes.
That is finite.
It is fine. You can't take it infinity. They can play. They can. So this why this relation becomes so simple, because first of all we have these linear laws, Newton's cooling law, and then we have these things constants, alpha, beta, like there. So now you can have n number required to include these things and get different. Yes.
What is this TJ?
There's pH, T hot birth temperature.
So you finally saying that efficiency with this assumption is 1 minus Tc by Th. It is not
Root over.
Root over. Right?
Yes.
It is not depending on the fluid
No,
temperature.
no. That is because of all the simplifications going in. Because of the linearity, the cooling laws, right? And then the endo-reversibility of the engines. That means that the fluid, in the typical engine, if you run the engine again and again, the fluid also heats up, right? But it is not assuming that. The fluid remains in the same, like on an average, I'm saying in a cycle. Okay?
No, but the thing is, if I take that limit such that, I mean, Th, you are creating a difference between Th and Tc.
Yes.
In this cycle, if I allow this Th
To be different from this.
to be equal to Th and Tc, like
No, so the point is like the fluid temperature, that is if you calculate if you have the entropy of the fluid, right? The entropy, the total entropy becomes, so the difference of total entropy in a cycle is 0. That's what it is assumed.
No, but for the Carnot engine, it is also 0, right? When it come back.
But then the Carnot engine, we don't have this temperature difference between the bath and the system. That's the major. So it has to be there. It has to be 0 because Carnot engine, the bath temperature and the system temperature are always same. They are in equilibrium. But here it is not. That's why it is not obvious that the entropy has to be 0 over a cycle. Change of entropy.
This is for Carnot cycle only, right?
No,
This is for this Purzo alcohol things.
Which is like a Carnot cycle.
Cycle is same, but there's a refined thing because you have included this. Yes.
I was wondering whether Stirling engine and things like other things will also have.
Yes. So there's a big literature on these engines. So this is just a beginning steps or so.
So my curiosity was based on at maximum power, which engine will be most efficient?
I don't know at this meeting. You can search. It's a huge, interesting topic itself. It is there. It is there. So it's a huge. This came out as 70s.
So one can generalize this.
Of course.
So only by first derivative, how we can say that this is.
People checked that whether second derivative, the negative and all.
So we have the form of that P as well.
Form of yes. We have a functional form of P in terms of all these parameters.
Okay.
Then we can minimize it, right? Or take the derivatives. Otherwise, I'm just not writing it. I'm just the essentials what you need to derive. No, this is macroscopic. I will be coming to the microscopic soon. So then we will leave this, how it is close to.
no, but this you maximize the power, right?
Yes.
So, I mean, maximizing efficiency is equivalent to maximizing.
No.
That's a
No.
different.
No. Not at all. There's a trade-off.
If
you, that's what Edgar mentioned. Always there is a trade-off between power and efficiency. You can't maximize both, right? So now I am coming to the stochastic things. So these are all macroscopic. Yeah, sure.
So here you are considering the loss of work, the heat transfer. There is the loss of work.
Yes, it is another very important assumption that adiabatics are assumed to be, in this particular case, reversible. Yeah. Very close. Of course, definitely. Setting up adiabatics is a very difficult thing, like in experiments in macro and micro both.
But and if it's quasi-static, then
No, not whole. This only this two.
Even if those two legs are balanced, then tau will be defined because it becomes detected.
No, not like that. So now, so we'll go to the first I would say that the first stochastic engine that is there in the Feynman lectures is the thermal Ratchet. So, but of course there are many other people use in a different ways. The basic principle that Feynman did in his book is there is a Ratchet system. So this is the first, I would say. So vein, and then I have a wheel, and there's a ball. So if I have all the same temperature, this fellow will not produce any work. But apparently it is kind of not so. So what is this ball doing? So this ball is rendering this wheel to go in the opposite. Like this rain can go, so okay, so there is a molecules here and they are always bombarding everywhere at temperature T. This is in microscale, very tiny. Now if I get a hit from this side, this vein, then it will go, say, for example, clockwise. If it is the hit from the opposite side, then it can go other way. But this ball, so the same thing, the wheel following the vein, it can go in this side or that side, but there is a ball which blocks one side. So that is why it says that it may do only one directional move, this wheel, and this can, if you have a pulley and a weight, then it can pull it up. But it is not the case, because this ball is also hitting, get heated from the same molecules at same temperature. That is why it lifts up, and then also it starts to signal with same probability. That is why it will not produce any work. It is given in this nicely demonstrated in lecture. Now the way out is what? Two way out. One is you make this all fluctuations out of equilibrium, not thermal fluctuations. Or you can make these wheels flashing, rocking, all sort of variants are there. And this is very, very useful model for motor systems. When you make these fluctuations out of equilibrium, not thermal fluctuations. This is one way to get work out of the system. The other way is make two different temperatures, T1 and T2. Okay? Then what happens? T1 is greater than T2. Fine? Now this fall, as T2 is less, it is less frequently coming up and down. So there is an average rotation in a particular direction of this wheel you may expect. And it is calculated in the reversible quasi-static case in Feynman lecture. It exactly, so the way is like e to the power minus, so say this is the load, so this needs energy E to pull, and so this is epsilon is the energy to for one wheel for one teeth of the wheel to turn. Okay, then epsilon plus E by sorry. So the rate of this rotation, or the inverse of the rate, comes from the Boltzmann probability in the reversible case. So epsilon plus E by E. So this is the temperature, yes, 1, and then e to the power minus, and this is the same temperature but without the load. So this is the T1, yes, and this is T. So in the reversible case, the probabilities these probabilities are same. This is the energy to turn this, to lift this up or down, and this epsilon is turning for one teeth or making the pen a little bit rotated. And if you calculate this one, you will get eta, which is epsilon over epsilon plus E, which is exactly T 2 by this current. Okay. So this device can actually work as a Carnot system in reversible case. You can show it. It is there. It is very, very simple.
Can you explain one more time?
Yes. So these are the, so in a reversible case, the rates or the probabilities inverse of that is Boltzmann. We are taking it as an equilibrium. Okay. Now this total energy is for this system, this vane and the wheel. Okay. What it does, it can turn single teeth and it can lift up. So both processes need two energies. One is epsilon, one is E. Okay. And this side is for the fall. It is turning up and down for epsilon, and it is for other temperature T2. And in the reversible case, they are same. The rates are same. Okay? You equate them, you get eta. Eta is this goes into the system, and epsilon, this fall, this is the cold bath. So this take this epsilon amount of energy. Correct? And you get exactly eta C. So now there is a difference. Of course, we get the efficiency here, true. But there is a difference, fundamental difference between this and this setup. One is the scale, of course. But the other is, see, this particular object, we don't have any piston-like thing. As Abhishek was mentioning, so this is kind of autonomous. If we have the system, put the temperature difference, you should, in principle, get this. There is no piston-like thing, which they need. The other thing is, you need to get the work out of it, you need to maintain a gradient of temperature. Temperature difference you need. Otherwise, you cannot get it. Is it clear?
Is that capital equal this
Capital?
efficiency?
No. Why? This is the energy goes in the system to carry the load and to make this rotate. And this is the work on heat or energy goes out through the ball. Okay? So why this kind of model, this T1, T2 model is not popular in biology? Because in the small scale, it is very difficult in the biological system to maintain such gradient of temperature. And there is no such, I guess.
But to maintain this gradient, you need to do some external work, right? And that is true for microscopic or
Microscopic are also there.
Also there.
Also there.
So, but this efficiency calculation assumes that is happening.
That is happening
at no cost.
No cost. Yes. Of course. So those things are similar in the macro, right? But the problem with this model, why the flashing or rocking kind of stuff is more popular in biology, because they don't need this to get work out of it. They don't need this gradient of temperature, and that is not there in the biological system, particularly small, and it's not possible to maintain.
But aren't biological systems driven by chemical potential?
Yeah, that is a good point. That one can, maybe there are calculations like that. Instead of temperature gradient, we can imply the chemical potential gradient, but how to recalculate this stuff, I haven't seen within using this concept of
But I
chemical.
don't think we should call it as a gradient, right? They are two separate paths. They are not connected to each other.
No, but this thing is simultaneously connected to T1 and T2. This object, this ratchet ball vane system, is has to be simultaneously connected, so there should be a conduction. Okay.
Sir, can you explain again why you equate the two exponents? Why did you equate?
This equality is for the quasi-static thing here, the equivalence. So in the reversible case, these two probabilities should match. you can just think of it. It will so the inverse of the probabilities are the rates. The rate of the rotation of this is like the ball thing. So think in terms of rates. That would be better.
So it's the inertia of the ratchet.
So there is no dynamical equation so far I have written because it is all in reversible. So you can't do the non-quasi-static things. Then you have to bother about the dynamics and all.
No, I mean, so here efficiency is 1 minus T2 by T1, which,
Right, yes.
which is equivalent to the Carnot.
Right.
And so here rate, I mean power will be very
Zero.
small.
Yeah, no, so you can, I think you can do a non-quasi-static thing also here, but people are more interested in having these wheels to be flashed and rocked because they are more useful in the biological systems, those kind of motor models. But this is, to my guess, is this particular, why I discuss this here, because it is in micro scale, it cares about the fluctuations, maybe equilibrium fluctuations, but they care about the fluctuations and we can get the efficiency out of it. So it is the first maybe demonstration, the stochastic heat engines that we are up to now. So now we want to make something like very analogous to this fellows, not this, because we want a piston-like thing which is absent here, and we need that these two paths, they are not simultaneously connected to the system, like here.
In efficiency, the numerator has to be capital E, right?
In efficiency,
Numerator has to be capital E, right?
capital why?
Yeah, because like efficiency will be useful one divided by total one.
No, this is that goes in the system because of this pulley and thing, and this goes out of the system. So this is input, this is output. Output by input is the.
No, I mean he's saying like 1 minus Q2 by QH is the efficiency, right?
Yeah, but this is coming from input and output things. This is this.
The work done and the total energy. Epsilon is the work done.
No, this pulley has to be pulled up.
That's what. No, that's what I mean. Epsilon is the work done, right? Epsilon will be the work done.
Yeah.
Work done. Oh,
So this
is the work done.
yeah,
Not epsilon is.
that is what the input.
No, that's what. So they are objective. If it's epsilon is the E is the work done.
No, I'm thinking about only these terms. Like this is the output, input and output things.
I think they are correct.
So then, what we will do in the micro scale, these two temperatures, the path, they will not be connected simultaneously to the system, like here. And there will be a piston-like mechanism. These are the ingredients to make a microscopic heat engine. The simplest possibility is what? Particle in a harmonic trap. Okay? So trap, that will be a breathing trap. It will act as a piston to the particle, and there will be a cycle where at a certain, say tau by 2, tau is a whole cycle time and tau by 2 is a half of it. Half of it is hot isothermal attached to a bath, TH, and the rest half will be attached to another bath. That is very, very analogous to this structure, not the thermal brackets system. Okay?
The motivation is not clear. I mean, this is also not possible. That is also not possible.
No, this is possible. That's what going to tell. It is possible, and that people made. The people who are making it is here. So this, okay. Say this is my half K. Okay. First, I will calculate is in quasi-static limit. In this particular case. So it will be like Carnot analog here. Half K square. It goes, this is a cycle. Then it is TH, isothermal, expand. Okay. So this is now half K square. This goes to here. Then Adiabatic expansion. So this is even more. So this is a particle, and you have half 1/4 K x square. Then this is DC, isothermal compression. So it means half K x square adiabatic compression. This is very, very similar to similar protocol that we have in case of Carnot. Clear? And the calculation for the time being will be quasi-static. Next class will be non-quasi-static. Okay.
So the vertical link, you call it adiabatic?
No, this is not like, this is just to build the cycle. So adiabatic, how to implement the adiabaticity, I will come to. Okay, this is just to the physical picture that what is the cycle. So this is the analog of this kind of heat engines. So first then start to calculate with work, all in quasi-static limit. So first step, which is isothermal expansion. So in isothermal case, we have the very standard thermodynamics, not much different from the macroscopic. So F we can define because it is also quasi-static. So delta F is delta U minus T delta S. So this is H, isothermal 0. So we have TH delta S, and now you have delta U is first law. From there, delta F is, so we just need to calculate the free energy difference in quasi-static limit. This all we do in the macroscopic case, so very, very similar, right? So W is delta F in the quasi-static limit, which means minus kVTH ln Z. So this is, say, my A, just do notation.
Sorry, Anna. Minus kVT of Z is the free energy. So you are doing the change to the energy. So exactly. Very good.
So you have said like pH isothermal expansion and now I'm trying to understand why you are saying let's say isothermal expansion.
No, there is this arrow is not that serious. It's just to represent the cycle. Nothing else. So I am not drawing the PV like diagram.
So you have changed the half k square, right?
I have changed the k to half k.
K to half.
Yes.
So
That's why I write it separately, just to what are the changes that I make. So k, half k, 1/4 k, half k, k. That's the whole cycle.
So what happened is that how you are saying that this is the equivalent to isothermal expansion?
Just I keep the temperature same. That's why. Like TH is, I'm attaching this particular system to a bath at TH.
No, I mean,
No, what is the confusion?
like this calculation, I'm trying to understand how this UTH necessity is being calculated.
Oh, okay. So this is TH. This is the derivatives, like differentials, and then I put it 0 because there is no del T. It's all isothermal. So I have this only this term, right? And this is delta Q in quasi-static limit. And then I have this first law. I use this delta Q.
This is,
there.
but is this has a connection with that? I mean, this is done.
This is macro, this is micro. This is true everywhere. It's all averaged. Means I can, if it is in quasi-static, what renders me to define delta? Nothing, right? Okay.
So that further reducing the trap stiffness by half has nothing to do with the
Here to here.
yeah.
No, that I'm not calculating now. I'm just concerned about this isothermal expansion.
And so that adiabatic expansion.
I will do. So this is, if you can calculate, this is very simple. Minus half mv square plus and in the downstairs we have x minus clear? Then I have, that's for W. If I do this is Gaussian integral, everyone can. So this is KB TH by 2 log. So this is the work done in the isothermal expansion. Is this side clear about my particular students? Is this okay?
Even in this case, there is that problem, right? How do you set up the gradient between the two paths?
No, I have only one path now. This particular calculation, isothermal expansion, only one path.
Yeah.
But there is a problem. There is a problem between the bath and the system. That I am as exactly the Carnot that we have done.
So there's TH and TC, right? So there's a hot path and there's a cold
No, there is no simultaneous connection. So once this particle is here, in this isothermal, then it is only there. There is no cold bath attached to the particle. Now you go to an adiabatic jump, and then you come to the cold bath when hot bath is not there attached to the particle. So that is what I am saying. Simultaneously, the hot and cold bath are not attached to the particle.
So the bath temperature is being switched.
Yes, exactly. When there is TH, there is only TH, no TC. In this calculation also. This TH is appearing, not TC.
So there will be some work done in that switching of temperature, right? On the bath.
This is the work done. Hello, yes.
Why would you need it piston like this? Like you were saying it for the
This doing this is similar to pulling piston.
No, but so we were extracting work from that pulley, like in the previous one, Feynman.
Oh, the Feynman was is different. That is what I am saying. That I am not following the Feynman case here. I am more or less conventional, following this.
But you were saying that we need piston for engines. Right?
No, we need means like in this kind of system, not in the Feynman kind of system.
We were extracting work because it was pulling up the.
Yeah. Well, that is that Abhishek mentioned. There is a hell lot of like autonomous kind of stuff where you don't need to push or pull like piston. They are steady state engines. They are not in this class. They are more or less in this class. Carnot class. Okay.
But then this need a exponential need a temperature.
Oh, okay. Sure. Good. Beta H. Yes. Okay. Then work along adiabatics. So how to first the question is how to set up the adiabatic part, right? So there again an idealization in this particular case. We go half k to 1/4 k instantaneously. How fast it is? That means your state of the system, which is defined by x and v, not changed. So the particle not even realized that my half k has become 1/4 k. So all its x, v, the probability distributions remain exactly same. That's how it is instantaneous. So basically, if you want to do an experiment, I would say that the relaxation time scale, the time scales involved in the particle dynamics, this time scale should be much smaller than the time scales involved in the particle scale. Okay, that's why it is instantaneous. Now,
Because, for example, if I am having a system and my particles are distributed along various energy states, and I am changing a external parameter so that the Hamiltonian of the system is changing. So, like in this change, if I assume like all the levels are going to the
so it is like an adiabatic. If you are saying, okay, I can just give an example of like a quantum system that like analogous thing. When you do the adiabatic thing, your operator changes, but your state remains.
Yeah, I mean all the states are there is no level crossing, right?
No,
not level crossing.
Not level crossing. Yes. The similar thing. So how to calculate? So now there is in this instantaneous change, the heat is exchange between the system and the bath is 0, which means that your W from first law is just the change of internal energies. Correct? Then you can calculate this W, average W. So there is some, okay, this is normalization of the probability. So what is the change? Change is half k by 4 x square minus half k x square. This is the change, and then you have to average over the distribution function. Distribution function is half beta, okay, mv square plus half k by 2 x square dx. See, the state of the system hasn't changed, the probability distribution also not. So I take this k by 2 here. So first change was what? K, 2k by 2, then k by 2 to k by 4 was instantaneous. Therefore, the distribution is not yet changed to k by 4, it is only k by 2. And the difference of the internal energy, it is not that the x is not changed, but as the k is involved in the internal energy, that's why I have to. Otherwise, means if you change m, then m, the kinetic energy should be there. But it is an ideal case, I am not changing m. So, but half k by 4 x square is the final, and this is the initial at the point where the isothermal ends.
The beta corresponds to h.
Exactly. Beta corresponds to hot.
In this case, spring constant has changed from k by 2
to k by 4.
So why we are just taking k by 2?
That is what I am just explaining. This is the distribution. The k by 2 to k by 4 is instantaneous. Distribution doesn't realize that this k becomes, this k by 2 becomes k by 4. Yes, exactly.
Can you write it here and you can make out one there in the bracket in the exponent?
If I can give a hack, no? Just follow the YouTube live stream, the board is clear.
Correct? This again, Gaussian integral you can do. This n1 is the normalization. If you do it, then what you will get is this minus, very simple answer, kbth by 4. So this is your adiabatic expansion work done. So W minus kbth by 4. Then there is just quoting the results here and then kbh.
Here temperature also changes from H to Tc.
No, it is adiabatic. So it is out of it is not in contact with any reservoir.
So,
but the TH is there because we ended in some isothermal. That's why TH is there.
So there will be the TC will be achieved,
but not through the adiabatic process. I have to end the adiabatic, then it will do. Yes.
Sorry, Anna.
And then you wait for long enough time so that it relaxes to it.
Yeah, in the quasi-static thing. So, but the long enough time, this time scale to relax is much shorter than the actual cycle time. Yes. So, the relaxation time that you are mentioning, it is much, we assume in this thing that is much shorter than the long cycle time, which is taken to be infinite, the whole thing. That is why it is quasi-static. Yes, Edgar.
Yes, so your adiabatic step is instantaneous or not?
Yes.
It is necessary.
It is. Yes.
So let me clarify. So the isothermals are smooth process, so they have finite time.
Correct.
And then the adiabatic is instantaneous.
Instantaneous.
I see.
Yes.
There's no time to dissipate.
No time to dissipate. That's what the logic. To stop the heat.
So is the model of Cypher in 2008 or is your model?
No, the 2008 contains more because they also optimize this protocol such that you can get what is the adiabatic heights exactly to optimize. There is no optimization so far. I will do it.
Okay.
Optimization?
So there is no optimization now. So optimization will come next class.
Just because it's instantaneous, just because it is instantaneous,
yes,
the adiabatic process.
Yes.
It's
just because it is instantaneous, that is why it is adiabatic. Okay.
That's why it's also beta H in both initial and final.
So, I mean, here you are taking the concept of inertia, right? It has some inertia, that's why it remains over there.
Yeah, but there is no dynamics so far, so I don't have any divinity term. I haven't written any equation of motion, but the inertia term, the kinetic energy part is there in the distribution. So now I have.
This will also come from the definition Abhishek said, d v by d lambda lambda dot.
Yeah, exactly. You can do that. You can do that. So you can write the differential equation, then to drop the divinity term to get it, okay, no. So it can come. You can show it later. Not in this method, but it will. So from the dynamical equation also you can get the quasi-static limit and derive this equation. This results. It's possible.
So work done is same in both isothermal and adiabatic.
Why? No. KBTH and this log 2 there.
Oh, earlier
it was W is a minus KBTH log 2.
Yes, written both of them.
Oh, okay.
that was the isothermal.
Yes, exactly. So then, very similarly, we can calculate the work. Isothermal compression. So after adiabatic expansion, there will be isothermal compression. So this is W plus kBTC, the core temperature, exactly same calculation. And then there is adiabatic. So this maybe students can do at home. That exactly very similar thing that I did here. You can do it in TC.
So this process is instantaneous. So how the system is in the equilibrium? It is like a quenching something.
So during quench, this is the only adiabatic quench. So we don't have to bother about the equilibrated with some path because it is saying that we are detaching the system from the path. Correct?
Yes.
So that's why, but it is, you are correct that it is not exactly. So here is the, so these kind of caveats is very similar to the caveats in Carnot that I mentioned. That's why I mentioned Carnot first. That there is a heat conduction that we are not taking into account. Or we are neglecting the other. That's why I mentioned Carnot. Okay? These are the caveats of this treatment.
That's still a question. You said that, the cycle time, that has to be typically smaller than the
larger.
That is
Much larger than the
Because
relaxation
it has
time.
to cool down to that temperature.
Yes, the RAT has to be much larger. In this limit, all the calculations are done.
No, but when you quench it, I mean, adiabatic process, you take it, and then when it reaches in that in the C point, so there it has, when you are waiting, some heat is being transferred from that, right?
Only if the V changes. We assume that it is so fast that V cannot change. X and V of the particle is not changing.
But anyhow, I mean,
Of course, in reality you are correct. It is there. It is there. We are not.
No, if after what you are calculating is the work done from C to V.
That heat that you have that quench done, then there is some. Those things is included here. I will calculate it. While calculating the heat, I will calculate after. So we need the heat also. This part and this part, right? So there will calculate there will be an effect of this quench. You will see.
But there, as a delta Q,
you will be there. It will be there. So then the adiabatic compression W, we exactly similar way we can calculate it. This kVt by. So the total work you see is minus, so this is total, okay? W capital T, W is by total, kVth by 2 ln2, this is from the isothermal expansion. Then you have minus kVth by 4, this is adiabatic expansion. Then you have kVt C by 2 ln2, then you have kBT. So this is the total work, correct? Now one non-trivial thing means which is not there in the macroscopic engines. You will see this work, whatever I calculate, may not be always negative. It may be positive, because if you rearrange the stuff, then you will see that this is
kb TC by 4.
First one, yes. First one 4 and then it is 2. That is why the problem. Means that's negative thing may come, positive thing may come. So the first, so you can rearrange the term kBTH by 2 ln2 minus kBTH by 4. This is always negative. Then I have, okay, let me write. The negative means yes. So you are extracting work. So kb, let me rewrite it. So this is from here. Okay, this is one part. The other part is minus kb by 4 th minus 2 tc. So this part is always negative. This part can be positive and making the whole thing positive. It's a possibility. Okay? You can calculate the bounds. Then when it becomes negative and when it becomes positive. So here it is very, very different from the macroscopic thing. Macroscopic, you set up for an engine, you will get an engine in every cycle. This is the not case here. So even if you put up an engine-like protocol, engine-like cycle, the output, as an output, you may not have the work. So you can just put some numbers. Say for TH is equal to TC, it is always positive, right? It is not, this is fine because, but say just put is equal to, TC is say 0.9 TH. It's a valid choice, but you will find a positive work here.
This is the
So,
upper limit. This is the lower upper limit.
No, you can calculate it, but I'm just doing some examples.
Okay.
So just a number, if you just put that, you will get some positive work output. Yes.
So the asymmetry is coming from these adiabatic steps, right?
Yes.
The PC by 2 versus the TH.
Yeah.
So physically, how can I try to understand
So this is
asymmetry as compared to the
not
macroscopic?
very these are the this will not be revealed in the quasi-static calculations. This will be like why it is like that. You have to take care about the fluctuations. Only average quantity will not tell you by which you get like so why so here is all I can say now. Whatever we have done is due to fluctuations, because in microscopic scale the fluctuations are very important. That is why it is happening. But why and how, that we need to calculate a bit more. Means I will may not be here, but we can.
No, but meaning in some sense we are ignoring something we should not have.
Yes. But no, we should not have. I mean, not in the approximations or something like that. It is there. It is even if you do the non-quasi-static thing fully, everything, right? Taking all the dynamics, you will get this thing. Even in the quasi-static limit, if you set as an engine, but you don't get engine as an output, you have some kind of limit.
So here we are in like over-damped regime.
No. It is, we have calculated all in terms of this.
No.
This.
I mean, it's just the potential energy.
Yeah.
There is no kinetic energy contribution.
Because our state doesn't change over the adiabatic steps. That's what we assume.
No. For example, say I didn't have any potential. I mean, it was just a square value, like the
Okay.
box, no x dependent.
dependence.
But then how can we introduce the piston-like feature? Like we are changing the
So
scale.
you can change the confinement.
Oh, acha. You have some trap, but
Yeah,
it's
but
square.
it's this shape, not
Right.
a parabola.
Right.
Then it doesn't have any potential energy as a function of x.
No.
Because like k is 0 for that.
No, but for example, if you have this old problems like quantum mechanics problem, you have this. If this is 0, this is some. This is v naught or infinity. Then this is 0. Then there is a space dependence here as well. So even if you put a box, there is a potential. You have to, even if you want to simulate, then you have to introduce the walls. So that is the thing.
So it is not, I mean, for some cases it will get positive or for some cases it will be negative.
Yes. That you can calculate. From here it is very clear. You can calculate the bound for which ratio of TH and TC you will get positive work or you will get negative work.
Has this been seen in the real experiments?
Yes. Yes. It is there.
With colloidal particles.
With colloidal particles. It is there.
Can you share the reference?
Better person maybe.
Okay, I will ask.
But it is there.
The real engine, at the end of the adiabatic process, the temperature is sort of matched with the cold bath. Here,
No, it is not matched. This will appear not just now.
I mean, in this, arbitrarily decided that the final K will be K by 4.
K by 4, yes.
If you tune that to be a function of TH and TC, can you make it?
Yes. Actually, this is precisely done in the Carnot engine in the experiments that Hitler talked about. That K is a function is now to make this thing real adiabatics, like on an average.
Use K by 4
Just for this is a kind of toy on the weakness.
There has been like this paper by Lecture-2 where they didn't have this like adiabatic expansion or something, but they were doing isoporic process and they were able to extract work. I mean, why are we considering like this kind of adiabatic expansion?
First is like it's very simple to calculate things. One, and the second is like it is always a problem. I kind of difficult. The establishing adiabatic steps is difficult either in macroscopic or microscopic. So there are many number of ways where you can implement the adiabatics. No one is perfect, so it is like that. So this is why I choose this particular way. Yes.
So at the final expression level,
you didn't see any like
everything is deterministic.
everything, but
right.
I have to calculate the average over some distribution. This I need. This I don't do here.
Yes.
That is where the microscopic comes.
Yes.
That is where the fluctuations come in terms of T.
Yes, but the averaging is already done.
Done. So these are all average results. The results are average.
What will be the average?
What is it? These are all average. But the microscopic system.
Yeah.
Because Edgar mentioned that experiments always do isoporic. If you do
No, not always. They have done. But there are like groups, they have tried to establish.
But if you do isoporically, then this problem will not be there. Then you will always expect something.
May not be there, yeah. That is possible. But there are different ways to like implement. We have chosen this way to.
But I'm confused. Like if you just draw PV diagram of any two isotherms and adiabats, you'll always get some finite inverse. I mean, how can it be negative? Like if you just plot two isotherms and two adiabats, you always get some positive area.
In PV diagram.
In PV diagram. But say I do the same thing with here.
But this is also the case here, right? That in the macroscopic also there is a PV diagram. We have this positive area, but then we get the negative work.
No, provided, but you said here it can be negative.
It is negative in some like the work done negative is extraction, right? We need to extract work from, this is the engine.
Which means the area is negative on the PV diagram.
No. This is a convention that the area, that whatever is there, it is a magnitude of the work. It doesn't care about the signature, whether it is extracted or, yes.
there is no PV diagram for this.
No, so what is the analog of B here?
Analog of this?
The PV diagram, like the K can be associated with the P. So what would be?
You can have this K.
So that is like P, right? The pressure. Generalized.
Yes, yes.
But what is the V?
Okay. X square average.
X square. So from that.
That's one. Yes.
So it is possible even in the experiments that we can change the spring constant, that K values.
Yeah, of course.
Instantaneously.
Instantaneous is always like with a pinch of salt, like because you are the dynamics of the particle, the scale there, your instantaneity has to be less than that scale. So that is what we are calling instantaneous.
In the thermodynamics limit, so there are large number of particles.
No, here is only one particle. This is a stochastic engine, right? So we started with a single particle in a trap. Okay? Single particle, but that's what people also do in the experiments. So now we can calculate the heat. Oh. Because we need to calculate heat, because we need to calculate the efficiency. So the heat to calculate the heat, we have Q is W minus U. W we already know in every steps. We need to calculate the internal energy difference from going from here, because we need to calculate this is heat intake. So from there to there. So now, actually not there, sorry, here. This step to this step, that is the isothermal expansion, we need to calculate heat. That is what we do here in tunnel. Right? So let's see how to calculate first. So delta U is integral half. So this is the, okay. So the final, so this is the point where I am calculating the UB minus UA. So what is UB? Average, all in average. So half K x squared. Then I have some normalization of probability distribution. Then x minus beta h half mv square plus half k by 2x. So this is only UB. Then minus UA. UA will be what? Integral half K, this was K here, x square into some normalization, this normalization constant, P minus, this will be what? So we came here via this, from this adiabatic jumps, correct? So we were in TC, so this will be C here.
Kinetic part you are leaving because of same temperature, right?
Yes. One second.
Kinetic part you are leaving because of the same temperature.
Kinetic part?
Potential energy difference. You are differences. You are not taking.
Okay, so this is K by 2 and this is K.
You are having half K square, right?
Yeah, half K square and half this half. This is here, na? This is half K.
So what I am saying is only the potential energy part of the particle.
Yeah,
Kinetic
because I can't change mass.
Right. No, not mass.
Here also x is not changed. I mean, x is changed from here to here.
That's fine. But I am saying internal energy of any system has two parts, kinetic and potential as well, right?
Hmm.
So kinetic you are because of the kinetic in the temperature is not changed, that's why you are not,
Okay, right.
taking half an
Right,
hour.
right.
The difference
Right. This is
will be
isothermal.
Right.
Isothermal process, exactly. But this thing I want to point out, this is beta C. Why? Because we were at TC and then there is an adiabatic jump, sharp jump. So the distribution is not allowed to change within this time. So initial distribution will be this. So actually it carries the heat thing via this internal energy, carries the information of like the change quench.
And you are not completing the cycle, right? Because A initially it is TH. You start this thing.
No, this is TH.
So A to B is isothermal.
This is TH.
You assume that A and B are at TH.
No, TH is also, the TC to TH is also simultaneously changed. Like there is a temperature cycle as well. So we just change the path as well. From TC to TH, that is also instantaneous. The velocity, this is a quench. We are talking about this. So this, as it is sharp, the state of the system is not changed.
I think in that equation there should be beta H in both of them, right?
Why?
Because both are at the same temperature.
No, but the distribution itself is different because there is a quench.
You are doing for adiabatic.
This is, see, here the distribution is with beta C, right? And then there is a quench.
That's that.
That is why I am taking beta C. Because the distribution here is beta C, with beta C. Because there is a quench here. This is beta C. With the distribution is with beta C. That's why I am taking beta C. Because before that we had a quench, we had a sharp thing. So the distribution didn't realize.
Because UB minus UA, that's why I got.
It is UB minus UA.
The state of A is you have K and TH. That is the state of A, right? That's how we define A state.
Yes. Yes, no, it is fine.
But then you calculate UB minus UA.
That is because, so the question is, what is the distribution here? Yes? This is what A. Now the distribution, here at the end point of this, the distribution was with TC, with beta C, that is with TC. Then the system faces a instantaneous jump, which it didn't realize that there is a jump. So the distribution is not realizing it. So the distribution is still with beta C here.
No,
but then you equilibrate that with TH.
So that happens here. And we consider the equilibration time, the equilibration that we are talking about, that is here.
The vertical jump is D to A, right?
Is
D to A.
D to A, right?
D to A. So your energy difference should be UA minus UD, right?
No, I have to calculate the energy difference B to A.
Sorry. So, okay.
B to A, because that is the intake. That will be that should go to the heat intake.
So why?
But the distribution here, I need to average U, right?
So for A, you are saying that
the distribution is there.
But that state was instantaneous.
Yes.
But the isothermal thing was.
Then because the U is the state function, right? So like two only, it depends on this and this point. So in the meantime, whatever the distribution, I don't care. The distribution here is same as distribution here because there is an instantaneous jump. That is why I use beta C.
But then
it relax.
So if the distribution is same as beta C, so then you have to say the temperature at A is also TC, right? Because that's the only way you.
Temperature is.
But then TC to TH, this process is not isothermal because you are equilibrating from TC and B you are equilibrating.
No, there is a simultaneous temperature is also changing by hand. Correct? So there is a TC, a TH here. Then I switch off the bath, say. I introduce another bath instantaneously, TC. Then here, I switch off the bath, instantaneously put another bath with TH. So it is TH, but the distribution is TC. So there is a difference between the temperature of the system and that is the distribution and the bath. right?
Actually, I think you are starting with a cycle. You are starting with a cycle when it reaches instantaneously. Then actually it will take some more energy from that energy.
That energy is there. If you calculate the thing, you will get.
But that you can take as a heat, and that heat can be included in the cycle from
So this
A
is
to B.
kBTH. If you do the calculation, it is like kBTH 3/2 kBTC. So this energy that we are talking about is encoded there because TC comes in the internal energy change between this and this. It carries the information of this jump because TC comes because of this beta C. You are.
No, I think some of the confusion is that when you draw an arrow like this ordinarily, I would imagine that A is an equilibrium distribution at pH and B is an equilibrium distribution at pH. And
No.
what you're changing is the K
not.
to K/2.
It is not that.
But you're saying that
It is not that.
the
So
case. So there are two
the-
variables I should think about: the temperature and the whatever the.
So
traps.
basically, just reframe the thing. The particle has some temperature, Tc, the system. The bath has other temperature, Th. Because it is isothermal, right? So that is why we are having this Tc and Th here both. Because initially particle has some temperature Tc and the bath is other temperature, Th.
Let's again go through the first cycle. So when you start with that time at A, step A, there the bath temperature and the particle temperature are the same, okay? That is TH.
The first.
Let's start from the beginning.
First.
It's TH. Then you go through the isothermal thing. Still, the temperature, there's no, I mean, it's the same for the bath and.
You mean the first cycle? I
Yes,
can
let's go
prepare
back to
the
first
thing.
cycle.
Yes. Okay. Fine.
Let's start from the step 1, A to B. Starting point, temperature of bath and this thing are same. You come here, again temperature is actually same because that's isothermal step. Then you make this adiabatic jump. So so here you say, so which one now one is changing, other is not.
Other is not, exactly. The adiabatic steps, this thing happens.
No, that's the isothermal step.
No, this one I'm saying. This is adiabatic.
Down here.
Yes, down there. This thing happens. Because your system has your particle has some distribution, bath has some
so
other.
So adiabatic, now you basically, the particle changes from that pH, the hot bath temperature, meaning whatever was TH to TC. Bath is still TH, but now you kind of allow it to relax.
Right.
The bath also comes to TC.
Right.
Now again, both the particle and the bath are at TC, right? When you are at step 3.
Step 1, 2, 3, yes.
Then you go to D.
Yes.
Here again, there is no, both are TC.
Both are TC.
Both are TC.
So there is a relaxation. So when this two temperature is different, when particle carries one temperature, the bath carries another temperature.
Yeah. But at D now we are both are again at
Where at D?
D, yeah. A to B to C, and then we are at D.
Right. Yes.
Now you go from D to A.
Yes.
Now
Then again this thing happens.
Now again the particle actually goes back to TH.
Particle
Goes back to TH, right? You are suddenly changing K.
No. Bath goes to TH. Particle becomes TC. Particle is at TC, right?
Yes.
Right? The bath goes to.
Because you have changed the shape of this.
Again the shape.
And then basically you actually allow the system to relax.
Relax.
And
In isothermal?
both are TH.
Right.
And then you continue with the cycle.
This. Exactly this thing happened.
So in this case, you've written UB minus UA, like currently add plus UB minus UC. That will be the
No. To calculate this, the motivation is to calculate the efficiency, right? So efficiency, the only Q in goes. So the definition of efficiency is that the W total by. That's why I am calculating this.
So why you are writing is equal to kBTH minus 3/2 kBTC?
That is coming from this to minus this. If you calculate this one, it will come. Because this has H, this has C. So both temperature comes in the internal energy difference.
Sir, if you are saying that in case of A, the distribution is similar to B, then why we are not using
In case of A, the distribution is similar to D. Yes.
Then why are we not using K by 2 there?
Where?
K there. Like you are using beta 3, then why K by 2 is not there? It should be K by 2. In previously we used
this is here. So but that is what the protocol. It is in my hand. I am changing it. So that here where this is beta C, but the protocol has gone to K.
But in case of when we were calculating work along adiabatic path B to C, we kept the K parameter as same in case of as B. When we were calculating
what work?
When we were calculating work along adiabatic path in B to C.
That is,
we kept it as it was in B.
Let me see. Work along adiabatic path we are talking about.
Work along B to C.
No, there was a difference between, so half K by 4 x square minus half K by 2 x square.
Yeah.
So there is a change. But the distribution contains K by 2 only. Why? Because the distribution is here.
Yeah.
But the particle didn't realize that we have to relax it into K by 4.
Yeah.
That is why.
Distribution is K by 2.
Yes.
Then it won't be saying D to A. The distribution is at D. Particle won't realize. Then it should be K by 2 there.
No, D is saying. D to A is it.
D to A.
Like you said in D to A.
That is okay. Let me see. This is the UB. So this is here. Okay. UA. UA is.
K by 2.
Okay. Right. Sure. No. Another problem. Why it is not K by 2? Because it has jumped there.
Yeah, but similar thing will happen.
This is right. I understand. So this is the distribution K by 2, right? Correct. The old distribution. Right. I'm very sorry. Right. Exactly. Correct. You are very correct. No, now you realize it. That is good. Yes, because distribution contains K by 2.
No, I mean that's fine.
It is K by 4. Yes.
Here you have calculated. I mean you are writing UB minus UA, but you are referring to UB minus UA, right?
No, UB minus UA, but the distribution is taken from here because of this chart.
Then K by 2 should be also there, na? In front of a question, it should be K by 4.
No, because I have already taken this one. It is only for the distribution. That's why I am giving time here. This is only for the distribution.
No, for example, then what will happen to that relaxation? Where it will be counted?
It's already counted here because it contains TC as well with TH. The internal energy difference is it's almost done. It's there. I just have to mention the diagrams and so now you have all work, heat, right? Then the efficiency is work by heat intake. That is there. I can, if you have the formula, I can write it out. But the thing that I need to mention it here, that here, if I can draw diagrammatically that, say this is hot bath.
What about Q out?
What about?
Colder temperature.
We didn't calculate it because the internal, the efficiency requires only heat in. We can calculate it in this way. It is not
The expressions in the same way, except for half temperature.
Both the expression means, yeah, almost same, but there is some subtle differences that we are talking about. This K by 4 is there in the distribution, and beta h is there. And then is beta t and k by 2. This is k by 4. This is also k by 4, yes. But the beta h, beta c is there.
Yeah, so final expression should be same except for half factor, right? And pH and PC. Where is the
pH and PC? No, I guess. So can we just calculate it a bit? Because the normalizations are there. So they can also, okay, we just calculate one, okay? Maybe, we just calculate it. So just last thing I want to say that this system, if I draw it diagrammatically, hold, and then I have hit QH, QC, then W extraction. This is one when with this, the limits, this TC by TH is less than 705. This all comes from the work thing that I mentioned. So there is a limit, so I'm just quoting the limits. You can very easily calculate it actually. So this is QH, then you get put work. So these are called pumps instead of engines. So this is QC, and this occurs, this is pump of type 1, say 705. Then I have this one is the pump that type. So it is so it is of course less than 1 and all. So these different types of these bounds are like verified in, you can verify in experiments. Okay? In the quasi-static, making tau longer and longer. So they are the limits. So within these limit we get different one type of pump, because why pump? Because you put work and get this thing hotter, and beyond that you put work and then both of the path heats up. Okay? So that is why we get 3 different kind of system, but setup is same. It's like engine and all. So these numbers are actually.
These numbers are when you go from K to K by 2.
No, it's for the whole system, the whole.
Like, but I'm saying that you are changing the K.
Yes, but this is the whole. This comes out from the whole calculation that when we have this.
True, but all I'm saying is when you do K to K by 2, suppose you hit 10.
Exactly. They can be different. They can be different. K by 3, K by 4, then things can be different. Of course.
So what do these numbers mean? Sorry, I missed that.
So this is the ratio of the 2 temperatures. When you are, so say you have this cycle, K2, K by 2, K by 2, K by 4, K by 4 to this, and the cycle that I described. If you have if you set this ratio below than this number, then you will get engines, even in the long. So this can be tested. If you then you have one type of pump, in other case other type of pump. Okay. So this can be tested in the lab.
No. So in the case of Carnot cycle, let's say we have a ideal gas. So in that adiabatic expansion and adiabatic compression has the work done is like balance each other. They cancel each other. That's why always that total work done is like negative.
Okay.
But here
no, but the calculation that here is very simple. you don't need, at least to arrive at eta expression, you don't need to mention, or you don't need a particular what kind of. So that was the whole book of Carnot, that he wants to show that there is some kind of universality in the expression of eta. Universality means it is apart from, like, you don't need to know the details of the working substance. So the motto was like that, without knowing or how far these details of the system, the working substance, needed to calculate this kind of efficiency, the form of efficiency, how universal it is. Then he finds this.
Okay.
So you don't need that part, means you don't need the
trap or
ideal gas as a working substance to arrive this. So that is what this calculation says. It just needed TS diagram. So I don't put any property, right? So that was the goal of Carnot, to show.
But here we have that system property, like that.
Here it is not that simple. Here we need a dynamics, we need a specific dependence on. So far, it is the status quo.
So pump 1 and pump 2 is different, like, because
you put the
heat is still going down.
So it seems like, so if I think about thermodynamics, right, so it should spontaneously flow from hot to cold, even when your ratio is between 0.7 and 0.89. But still we have to do work on that process. Does that?
Yeah, it is like still we have to.
Against the first law?
No, whatever you put W, it got splitted into. No, sorry. It's so that is that. So you are, the heat can flow from here to here without this. That is there. But if you put then more here. So this is not against second law.
You're accelerating the flow.
Exactly. So it's something more there. If it is not that, is there. But if you put more, get more. So here I stop.